Welcome. This is the obligatory slide. So yeah, ask a question through the app and rate the session. Thank you. We're going to talk about just machine learning and your first steps into the world of machine learning. So if you already involved in machine learning, you might as well leave, because everything I'm telling you, you already know. So my name is David Stibbe. I'm a developer for Quintor. Quintor is an agile consultancy agency which specializes in .NET and Java. You can Twitter me at my handle. Yeah, I'm a father of one little AI, and another one is on its way soon. So today we're going to talk about intelligence, artificial intelligence, machine learning, how those relate to each other, what methods are used in this area, how machine learning is applied in everyday life, a small section, and how to get started, so how to get yourself on your way eventually. So intelligence, artificial intelligence, and machine learning. Let's have a quick introduction. Machine learning, yeah, it sounds quite scary. Nobody really knows what it is, but it is very popular in the media. You see it everywhere in articles, in newspapers. Machine learning this, machine learning that. How do you teach a driverless car to drive, etc., etc. And it's also, yeah, you can find it on Netflix, for example. Most of you probably already know, but when you view a movie like Arrested Development, it usually gives a suggestion about, well, you've seen Arrested Development, they must like Legally Blonde and Bob's Burgers and some other movies. It doesn't just do these recommendations nilly-willy, it does this based on, well, millions and millions of user inputs from other accounts, and uses machine learning to make these recommendations. Other way in which it participates in real life is your mobile phone. Everyone has one. For example, your Google Assistants, your Cortana, your Alexa, or your Siri. They're all basically smart digital assistants, which are capable of voice recognitions and capable of parsing simple questions. For example, who played James Bond in Quantum of Solace? And it's capable of answering that it's Daniel Craig. But it was also capable of answering is, what other movies did he play? However, this is quite a more complex question for the simple fact that it requires context. For he refers to the previous results. So it needs to know what the previous results were before it can answer that question. Now, nowadays, those digital agents are quite capable of answering those questions. And also this is because of a copious amount of machine learning. Intelligence. What is intelligence? Well, most of you guys know this, but it's basically the capability of reasoning and solving problems. Artificial intelligence is simulating this through computers. So a computer who's capable of reasoning and solving problems. It's a big problem domain, and it's divided in several, actually quite a few subdomains. These are 4 of these, just a subset. For example, natural language processing. That's the ability that you're capable of processing natural language by a computer, and is capable of interpreting exactly what you're saying. Knowledge representation would be the problem domain where you have to have a computer resemble internally the knowledge of a certain problem domain. For example, medical assistance. It would have to have a model internally from which it can deduce solutions and problems. Automated reasoning, that means that you're capable of coming up with new solutions, original solutions, for example, for puzzles, and also for common day questions. For example, if you're at home, at work, and Google, of course, knows this. Google knows where you are. And he noticed also that your Wi-Fi at home is in use. Well, Google should be able to deduce Well, that is not supposed to happen. You're not at home. So it should be able to alert you and inform you about these things. But what we're going to concentrate on today is machine learning. Machine learning is the area where actually a machine is capable of forming its own solutions to problems. A short history of machine learning will be to start with the Turing test. The Turing test was devised by Alan Turing in 1950, and it's basically where there's an operator sitting behind a screen and conversing actually with someone on the other side of the screen. And on the other side should be a computer or a human. And the idea is that the computer should be able to fool the human into believing that he is a computer. If he's capable of doing that, then he's smart enough actually to be called intelligent. And, well, Alan Turing would, that's what quote of Alan Turing, of course, a computer would deserve to be called intelligent if it could deceive a human into believing that it was human. Now, 1952, we already had the first AI application. Actually, Arthur Samuel implemented a game engine, actually, AI, which was capable of playing checkers, using thousands of registered checker games and having the application learn from those games. Well, fast forward 45 years to the future, or actually almost 20 years in the past. In 1997, IBM Deep Blue defeated Kasparov. It was a big thing back then. And at the time, it was thought, okay, we made big progress, but for example, the game of Go, which has much higher complexity, is way, way in the future, decades. Well, there was another big breakthrough, actually. In 2011, IBM Watson was capable of defeating its opponents in Jeopardy. Jeopardy is basically a game quiz. An answer is given, and the contestant has to give the question that belongs to that answer. And the difficulty is you have to actually first know the context. You have to be able to formulate correct sentences, so all adjectives, nouns, pronouns, conjugations do have to be correct. Oh, and you need to know what you're talking about. So it was an impressive feat. However, even then, Go was still a long way. Well, actually it wasn't. In 2016, most of you know, Google DeepMind defeated Go champion Lee Sedol, and actually did so 4 times against 1. And actually now they already retired it, but basically that was a breakthrough, because in 2015, they thought it would still be decades away. So it's like having a flying car being able for pre-order tomorrow. It's really impressive how fast that went. Well, that was a short introduction about the history. What kind of intelligence do we have? We have consider weak AI and strong AI. Strong AI usually means that you have artificial generic intelligence. Basically, that means you have artificial intelligence at a human level. You're capable of reasoning over several problems domains, and you're not stuck on only checkers, for example. Weak AI, on the other hand, is really, really specific. It means that the AI is basically capable of performing one task. For example, checkers, or chess in this game. So, as we saw in the history of AI, there was suddenly a big progress. First, it was 45 years. Then suddenly, within 17 years, everything changed. How was this possible? Well, the first thing would be big data. We have now such copious amounts of data that we're capable of actually training these algorithms that we want to use for AI. This was actually in 1997 really unimaginable that there would be a Google which has warehouses and warehouses and warehouses of computers storing data with cat pictures. On the other hand, we have big compute. This basically means that we have also large data centers of computing power, cheap and specialized. Another one, less known fact actually is the advance in algorithms. So excuse me. So, what's the advancement in algorithms? When I studied in 1999, neural networks were basically, well, nice, but not really feasible due to the fact that it was slow. It took a lot of computing power and time to train such a model. However, in 2006, there was this person whose name I forgot, sorry, who actually revolutionized a part of the training mechanism in neural networking, making it possible actually to use neural networking. In 2010, this already was redundant, but it gave a new boost to neural networks and making it possible to actually use these. The other one is the fact that there are several companies now heavily invested in machine learning, throwing big money against it and really putting time and effort in it. So these factors combined is why AI is all of a sudden, let's just say the past 7 years, making a really strong return. Machine learning. How does machine learning differ from normal programming? Well, most of you know. But basically, machine learning, it means that in regular programming, you have data, you have your program, you feed them to a computer, and you get output, basically. Machine learning is a little bit different, of course. You have data, you give it a certain output that you expect for that data, and the computer is supposed to, well, produce a program that would solve that problem for you. So you're not actually doing everything by yourself. For example, well, we have an apple and we have oranges. You can't really compare apple and oranges, but let's try. How would you differentiate these? Well, first of all, I would think color. So, but what if it's a grayscale image? You would try texture. What if you add bananas? Well, you would have to add another exclusion, another exception, etc., etc., etc. Eventually, you get a whole bunch of code which is actually unmaintainable and will never be actually fully covering all areas of fruit. So this is where machine learning comes in. You train it, and it will come up with the answer program itself. So what methods of machine learning do we have? We have supervised learning, we have unsupervised learning, and we have reinforcement learning. Semi-supervised learning is basically a halfway solution between supervised learning and unsupervised learning. We will discuss each of these in the coming slides. Supervised learning. So what is supervised learning? Supervised learning means that you have a machine learning algorithm which you feed input and keep training it on that input. Each time you give it input, it will give a prediction, and then you tell it whether the prediction of a certain label, for example, is right or is wrong. If it's wrong, it will adjust its model. And you keep repeating it till the error is low. Eventually, well, you extract a classifier model from that machine learning algorithm, because that's what it's all about, and you put it in your program and use it. You give it input, it will give a prediction. So what the main algorithms used, what it's used for supervised learning, classification and regression. Classification actually means that, let's say you have two features. Feature is actually the aspects of an input on which you want to train the model. So feature 1, feature 2, and it tries to classify each one. And for regression, it's usually you have a feature, set, and you have value as an output, and you want to have it estimate which value it might occur if you give it an input. To clarify this, for classification, for example, we have a data set of houses, and we're going to classify, going to train it on classification, whether something in a house is cheap or a house is expensive. So as input features, we use living area, and we use price. And we give it keep it training, and each time it will tell, we give it a house, it'll say, it's cheap, it's expensive. We say, no, you think it's cheap, but it's expensive. And it will adjust this model. Eventually, we'll have a model that can separate houses based on the living area and the price, and determine, yeah, that's cheap, that's expensive. Regression, on the other hand, works a little different. Let's say we have the living areas and the corresponding prices. And we keep telling it, we just give them the data. What the idea is then, eventually it will have a function that will actually match living area with the price. And if we have the model, we can give it just the living area, and it will produce a price for us, an estimation of the expected price. So in short, classification would label it, and regression would try to estimate actual value. If there are any questions, do ask, please. Well, for this problem, we use neural networks, usually. You can do it in other ways. I've not seen it, but you could. A neural network is based on the biological neuron. It looks schematically like this. Inputs for a neuron come through the dendrite, so top left. It will go through the nucleus, and it will give a signal based on the inputs through the axon to the axon terminals. Quite basic. In computer science, you would model it like this. Basically, these are all the inputs. Each input has a certain weight, so importance. It will sum the weights times the input, make a summation of that. And then it will determine whether or not it will output a signal and how strong that signal will be. So that will be the activation function. Well, combining all these networks, you will get something like this. This is a three-layered neural network. You get the input layer, you have the output layer, and you have a hidden layer. It's called a hidden layer because, well, nobody sees the hidden layer. You only see the input and output as an outside view. And this is fully connected to the network, so each neuron is connected to each other neuron. To make this a little bit clearer, I would like to demonstrate this actually through something called Tensorflow Playground. Who of you have already played with this or seen it? A few hands. Well, this is a really nice tool. It gives you an idea about how neural networks work. You can play around with it. I created a matcher for a spiral here. But let's just, it's a very handy tool for visualizing, I think. So you can determine here whether you want to classify or regress. For this input, we take the two coordinates of each point. So x1, x2, so the x and the y coordinates. And we're going to train it. Well, don't have any hidden layers. Well, that's a nice separation. We don't need hidden layers for this. So let's make it a little more complex. So you have 4 groups. Basically, orange is here, blue is there, and blue is there. Let's try to train it. Well, it's not going to match, is it? So we add a hidden layer. Let's see what it does. You will see that suddenly these lines color up. Basically, the thicker the line is, the bigger the weight. If it's blue, it's positive. If it's orange, it's negative. And these blue-white divisions that you see here on the neurons are basically the activation functions, the representation of the activation function. Basically, if you see blue here, it means everything that comes in this area would be positive, and the rest would be nil. So this is not going to work, this separation, so let's add some extras and train it again. So a few extra neurons, and suddenly it's capable of really dividing and classifying the outputs. So this is clear for everybody. I'm just wondering. Okay. So in deep learning, well, deep learning actually means nothing more than that you use a neural network that has more than one hidden layer, nothing else. So this is deep neural network because there's 3 hidden layers. Well, this is an example of how, in short, these layers would represent each activation method. So let's say you have an input layer, which is a picture, because you want to categorize between cats and dogs, we input the human face. And for each pixel, we input a neuron. So let's say this is an 18 by 18 pixel, 12 by 12. I wouldn't know how many nodes it would be, but plenty. In the hidden layer, we get actually the edges first. Then later on, you'll see that it's a combination of edges. So the nose, the eyes, and after that, in a layer later, you see the object models coming out. And a nice one would also be, online you can also find the Inception model. The Inception model is a vision model, pre-trained vision model from Google that they released. That you can just use, play around with. It's quite complicated, the model itself, it's this big. And they also made a project, someone did, from Google Inception, which actually shows actually all the layers, and shows you how this would look, as we just shown before, on a real neural network. So these would be, on the first level, the separators. And if we look at the output after the first layer, I don't know whether you can see it, but this is basically a heat map of what is highlighted of the dog that you saw previously with regard to the edges. So you can see here a bit of the shape of the dog, here. It's interesting to see. I would recommend looking at it. By the way, this is a Python notebook. Many of you probably have heard it in the previous sessions about it. I would really recommend using it because maybe if you use Mathematica or something, this is basically the same principle. You can just write text, put in code that you can reuse later. It gets explained, it gets shown, and it's executable. Continuing. So there's not just one neural network architecture. There are quite a few. This is from the neural network zoo. And it shows, well, that you really have to consider what kind of architecture you would decide upon if you want to build your own neural network. So there are several frameworks that already provide trained models through an API. Trained models, some through an API and some don't. For example, the Google Cloud Machine Learning Engine. You have the IBM Watson Machine Learning. That's through Bluemix. Microsoft Azure Machine Learning. Recently, Apple also introduced their own machine learning for your applications. Cafe 2 has a whole model zoo, which you can download and use. But the first 4 actually provide APIs that you can directly use in your application. IBM Watson was, by the way, a byproduct of IBM Watson. Of course, after they did the Jeopardy thing, they had a very nice question-answer mechanism, but they also learned a whole lot and provided those API for the public. So, like, they have a vision API, voice recognition API. Well, the same goes for Google Cloud and all the others. But it's very nice. You can play, for example, for the Google You can play around with Vision API. You can just, well, let's just take my daughter, for example. It's very nice. So you can just upload it, and will detect actually everything. It will show you. It will say, I have no idea what her emotions are. No joy, no sorrow, no anger, no surprise. She's like, none, emotionless, apparently. Yeah. She's apparently a person, infant, child, skin, and for some reason, Google thinks it's a day. Though most of you probably see it's night, inside, lights on. So it's very nice. You can just get an account for free. It's very fun to play with. And you can just call it through REST API from your programs. All right, that was supervised learning. Unsupervised learning. That basically means the opposite of supervised learning, of course. What this means is basically, I have a bunch of data. I have no idea how the structure it might be. I have a machine learning algorithm. I just give it to the algorithm and say, okay, you try to sort this out. I'll come back later. And after it's done that, you have a classifier model. It can give it input and will give you more or less where it expects your input to belong to. So there are mainly 3 algorithms that are used for this. Clustering, when you try to find similar instances. So these are the instances. These would be features, so the aspects that you put into it. And here you see, okay, these 3 instances have the same features. These belong to each other, together. Anomaly detection, well, everything here would be white, and there's just one entry which is completely different than the rest. Association discovery, that's when you basically see, okay, for example, these 3 instances have feature from the 2nd column, but they also have all features from the 4th column. Well, an example from practice would be, let's say you have a food web shop, and you notice everyone who buys buns and salad also seems to buy burgers. That will be association discovery. So when someone buys salad and buns, yeah, there might be some burgers involved. For clustering, by the way, it means that you don't change the data set or you don't go grouping it, but basically you try to find where the clusters are. So this is basically an example of k-means clustering. Means you, before you start, you say, okay, I want to find 3 clusters. That's the k, 3. And I'm going to start at random. I just point here, there, and there. And then I'm going to try to shift those mean points of the clusters, the center points of the clusters, until the distances of points become minimized. And keep iterating that until there are no changes. So keep shifting the mean points, those are these, till it found the best solution for 3 clusters. The downside is you would have to know that there's 3 clusters in advance. That's a bit of the danger. Well, we also did it at Quintor for Toolmax. We offer products by customer profile. So we also did clustering based on category, manufacturer, postal code, and eventually we were capable of actually making product suggestions based on what they were searching for. So for example, there was a probability of 0.90% that product ID 11807, which is the SCS plus drill set, should be recommended. So, okay, that was supervised learning. We had unsupervised learning. And now there's reinforcement learning. What is reinforcement learning? That's when you have an algorithm that can perform certain actions. For example, a game, you can go left, you can go right, maybe you can shoot. Each action has an effect on the world. And as a return, you get a reward, increasing score, for example, and you get a new status. You moved right. You're not at the same position where you were before. Well, a nice example is actually this game. It's most of you know, right? Breakout. It's an Atari game, and it was actually used by DeepMind before they to train their models using reinforcement learning. It's also one of the reasons Google bought them. I would like to show this up. So, well, awesome. Yeah, okay. So basically, they just took the pixels of the screen as input and the score. That's all that was input for the model. Nothing else, just the score and the pixels. And he knew what he had to do, left or right. But, okay, it starts 20 minutes of training. Basically, he sucks at it. So you see, man, sometimes he does hit the ball by coincidence, but man, it's not very, very proficient. See? Yeah. But after 2 hours, he played like an expert. So he had no problems. So I'm going to skip forward, can I? So he's pretty good. I would have problems beating him.
That's because the reward changes the model?
Yeah, the reward changes basically the model. It's based on the Markov decision process, and I'll get back to that in a second. After 2 hours, actually, something special happens. He finds out that there's an even better way to score points. It's basically by tunneling, which you'll see in a second. So, it's pretty good. So, yeah, basically someone asked us, yeah, he'll update his model basically by the rewards he gets. So try game after game after game after game, and he makes a decision tree, basically, and each decision he makes has a certain probability for a certain reward. And he keeps updating it based on experience. And eventually, it does pretty well. And DeepMind did this for all kinds of Atari games, and actually showed that there's basically a possibility for generic intelligence there. For the fact that there was no domain knowledge previously involved, it was capable of solving various tasks for all kinds of Atari games. But there's also, you could say a subset of reinforcement learning. It's called genetic algorithms. Most of you have heard about it. Basically, it doesn't. It's a little bit different. Here you take one model and you keep training that. Genetic algorithm works a little bit different. There's a nice example on the internet. Not this one. Yep. I wonder how he trained, by the way. Still sucks. Anyway, this is an example of a genetic algorithm walker. Basically, what it does, every generation, he throws out 10 models. Based on how far someone gets, so how much reward he gets in one model, one run, it determines who lives and dies and who may reproduce. So, for example, I've configured this one from champions to copy, 2, if you see it there. So, only if you win the game in your first 2 positions, you just go on to the next round. And the rest of them either get killed off or are being crossed over. So basically, properties from one model will be combined with properties of other models, and thus optimizing or making it worse. Depends. And each time you keep going on and on and on, and keep track of the optimal scores. So, also, there are a lot of algorithms to choose from, so it's really important to have a grasp on what you want to solve, how you want to solve it, and what you need to solve it. So, how is it applied in everyday life? In short, you can see several applications already running with it. Weather forecast for Amsterdam. Here's a filtration system that actually can predict whether or not something is going to fail or something needs attention. Automatic translation, so this is actually several problem domains in one. So you have image recognition, then you have translation, then you have to redisplay that translation on the image again. So, and this is actually cancer detection. So, on a very low level, determining what's the probability that something may be out of place. Spam filters, of course. And the Tesla car. So how would you get started? So I'm going to be very short with you, but there's basically two ways to get started. Either you just use the pre-trained models, like the Fission API I just showed, just use it in your application, and, well, don't reinvent the wheel, for the simple fact, yeah, there are people out there that did it before you, and you probably are not going to do it much better. So, as I mentioned before, there's Google Cloud ML, IBM Bluemix, Microsoft Azure, etc., etc. Or you can build your own and tweak with your own, but then I would suggest, first of all, learn Python. Yes, you can use most libraries with Java, Scala, I love those, but basically the data science and machine learning area, everything is Python. So every example you'll see is Python, every notebook you'll see is Python. So at the beginning, just learn Python, and if you're comfortable enough with everything, maybe then move on to another one, another language. Install Python Notebook, really, install it, and try the online guides. There are plenty of them, they're very good, and you'll be a fool if you don't use it. Well, for example, machine learning libraries that you could use if you want to do it on your own are Tensorflow, TF-Learn or Keras, Torch, which is Lua, Tiana, Python, Deep Learning for J, someone did do it, Java, and Caffe 2. And there are several others, but these are the most. For those who are wondering really what is TensorFlow, in the basics, it's a graph-based calculation framework. So the libraries on top of it support machine learning, but in essence, it's a graph-based calculation framework which optimizes for parallelization and other things, like running on the TPU, GPU, parallelization on several processes, etc. Well, also, if anyone saw the talk yesterday about the data analysis, yeah, it is a very important aspect. First of all, you want to frame the problem, identifying what you want to solve. For example, with the housing data, yeah, what do you want to solve? Do you really want to know the prices, or just do you not want to know how expensive it is? Or is it expensive or cheap? So you have to adjust the data as well, clean it up, filter it, and adjust it where you need. You need to look at the bigger picture. Basically, what's coming before and what's coming after your machine learning. So the reason why you predict housing prices is not because you're such a fan of houses, usually. Usually it's because there's another process after you which really needs that information. Well, third point, check your assumptions, because you have those and they're usually wrong. And visualize. Again, the Python notebook. If you have an idea for a model, if you have an idea of how the data set should look, if you think your machine learning should work, visualize it. Visualize every step, see how it outputs. Don't put it in your application at once. The future of AI. Well, as we saw, it went quite rapidly in the last few years. So rapid that it's unimaginable, actually. For example, this is the police agent from Dubai. In 2030, Dubai is intending to have, I believe, 50% of its police force replaced by these things. However, it's no more than a walking kiosk at the moment. On the other hand, we have Boston Dynamics, which is actually a ex-military contract from Google, and these are no jokes. And another thing about what Google recently released is, for example, 2 papers regarding relational networks. So these are special networks that want to have pluggable in other neural networks, which you want to use to answer a question like this. There's a tiny rubber thing. There's the same color as a large cylinder. What shape is it? So, tiny rubber thing. The same color as this big thing. So, for us, it's already a few steps. And actually, they proved that they were capable of answering this question with quite better than human proficiency. So, yeah, we can expect a lot more in the near future regarding this. So here's some resources also that you really should check out. I really would suggest look. Another one, good hands-on, is actually this one, Aurélien Géron. I probably pronounced that wrong, but he wrote a whole book, put his whole, all his notebooks online on GitHub, and gives you really a good introduction into data science, scikit, TensorFlow, all those things. It will take time, but, sorry?
Is that the O'Reilly?
It's also the O'Reilly book. He published the O'Reilly book. Yeah, the scikit, I don't remember the title.
It says Introduction to Machine Learning with by scikit and TensorFlow.
Yes, I don't know whether he said introduction, but basically, yes, scikit and TensorFlow. It's this big, thick. It's a good read, though.
Yeah, he writes in a very accessible style.
Yes, and his slides really represent this book as well. So it's really, really important to look at this if you want to have anything. So these are some other miscellaneous sources. ImageNet, this is, for example, resource for all kinds of images and computation, basically, to check how good your image recognition is. OpenAI is a platform promoting OpenAI. And they also have an OpenAI gym for competing for several problems. And what I just showed you, the genetic algorithm walkers, which is basically simple genetic fun. Any questions?